All right, everybody, get ready. Because today we're taking a deep dive into a world that's, well, a little strange, to say the least. Quantum physics.
Yeah, we're dealing with some pretty mind-bending stuff today, stuff that really makes you question what we think we know about, well, reality itself.
Exactly. And to help us navigate this world, we're cracking open a textbook that's, well, let's just say it's not exactly light reading.
Yeah, but no worries, we're here to sort through the dense stuff and pull out the really interesting, mind-blowing parts for you.
That's right. We're on a mission to uncover the real deal in quantum physics, the stuff they don't always tell you in those simplified explanations you might have heard before.
We're going deep.
Deep indeed. So let's kick things off with a question that's had philosophers and scientists scratching their heads for centuries. Is light a wave, or is it a particle?
A deceptively simple question, right? I mean, it's light. How complicated can it be?
Well, pretty complicated, apparently, because even big names like Newton and Aristotle couldn't agree on an answer.
Yeah, it's pretty wild to think about something so fundamental to, well, everything we see could be such a mystery for so long, right?
Absolutely. So how did they even begin to try and figure this whole wave-particle thing out? What was the turning point?
Well, for a while, there was Young's double slit experiment. Picture this. They shined light through two tiny slits, figuring, okay, if light's a particle, we'll see two bright lines on the other side, right?
Right, light travels in straight lines. Or so you'd think.
Exactly. But that's not what they saw. Instead of two neat lines, they got this pattern, kind of like ripples on a pond when you throw in two stones, an interference pattern.
So that's where the wave idea comes in.
You got it. Because that's how waves behave. They interfere with each other, creating these patterns. It seemed like a pretty solid case for light as a wave, right?
Yeah, case closed, right? Light is a wave, end of story.
Oh, if only it were that simple. Remember, this is quantum physics we're talking about. Things are rarely straightforward. Turns out, light can act like both. A wave, A and D, a particle, depending on what you're looking at, how you're looking at it.
Okay, now you're just messing with me. How can something be two completely opposite things at the same time? That's where I get lost.
It's one of the big head scratchers in quantum physics, for sure. Wave-particle duality. The way to think about it is that light carries energy in these little packets, these bundles of energy called photons.
Okay, so like tiny billets of light.
Exactly. And we can actually see this particle-like behavior in action with something called the photoelectric effect. Shine light on certain materials and it can knock electrons right off. It's like those photons are little projectiles colliding with them.
So where does the wave part fit into all of this if we're picturing these photon torpedoes?
That's where that double slit experiment comes back in. Even though light acts like a particle, it still creates those wave-like interference patterns. It's like each photon goes through both slits at the same time, even though it's just one particle.
Wow.
Wild, right?
Hold on. My brain needs to catch up. So you're saying each photon is kind of doing a split, going through both slits simultaneously, even though it's just one thing?
You got it. And it's not like it's switching back and forth. It's more like it's embodying both aspects, the wave and the particle, at the same time.
So light is playing both sides, huh? That's pretty incredible. But is this whole wave-particle duality thing just a light show, or are we in for even more weirdness?
Oh, there's always more weirdness. Buckle up, because it's not just light that behaves this way. It's everything. Electrons, atoms, you, me. We're all riding the wave, so to speak.
Wait, I thought we were diving into the world of tiny particles, not suddenly turning into surfers. You're saying everything has a wave-like side? That's a lot to process.
It's definitely a concept that stretches our imagination. Think of it like this in the quantum world. Things aren't as clear-cut as we perceive them in our daily lives. It's not that you and I are literally rippling through space.
That's a relief. I was starting to wonder if I needed a new surfboard.
But on a fundamental level, we can describe everything, even you and me, using a mathematical representation called a wave function. This wave function represents the probability of finding a particle in a particular state.
So instead of picturing an electron as a tiny ball whizzing around, we should be thinking of it more like a blurry cloud of possibilities, with the wave function telling us where it's most likely to be.
That's a great way to visualize it. And this inherent fuzziness leads us to another mind-bending concept, Heisenberg's uncertainty principle. You've probably heard of it.
Oh yeah, it's the one where you can't know both the position and momentum of a particle with perfect accuracy, right? Like, the more you try to pin down one, the slipperier the other gets.
You've got it. And what's even more fascinating is that it's not about our measurement tools being imprecise. It's a fundamental limit baked into the fabric of the universe. It's like the universe has a cosmic rule book that says, you can know this really well, Or you can know that really well, but you can't know both at the same time.
So it's not just that we haven't figured out a way to measure things perfectly, it's that this uncertainty is built into the very nature of these particles. That's a game changer.
Exactly. And it has some profound implications. For instance, remember how in classical physics, electrons should theoretically spiral into the nucleus of an atom because they're constantly losing energy?
Yeah, that always seemed a bit unstable.
Well, the uncertainty principle explains why atoms don't just collapse. Because we can't know both the position and momentum of an electron with perfect precision, it's like it's smeared out over a region of space. This prevents it from ever being precisely located at the nucleus, which means atoms, and therefore matter as we know it, can exist.
Wow, so this fundamental fuzziness is what's holding everything together. That's huge.
Yeah.
I'm starting to see why quantum physics is so revolutionary. It's like peeking behind the curtain of reality and realizing the universe has some pretty weird rules.
And believe it or not, it gets even weirder. This uncertainty, this blurriness we've been talking about, is actually what allows for the mind-boggling phenomenon of quantum superposition.
Superposition.
Yeah.
That sounds like a superhero power. What does it entail in the quantum world?
Well, in a way, it is a kind of superpower for particles. You see, because of this inherent uncertainty, a particle doesn't have to choose just one state. It can be in multiple states at the same time. It's not just that we don't know which state it's genuinely in all of them at once until we make a measurement.
Okay, you're blowing my mind here. So it's like a coin spinning in the air. It's not heads or tails until it lands. It's somehow both at the same time. But how do we even know that's happening with particles?
We have experiments that demonstrate it quite clearly. One famous example is the Stern-Gerlach experiment. Imagine you have a bunch of atoms and you send them through a specially designed magnetic field. Now, these atoms have a property called spinel. You can think of it like a tiny internal compass needle.
Okay, so they're like little mini magnets.
Exactly. And depending on which way this compass needle is pointing up or down, let's say the atoms will be deflected differently by the magnetic field. Now, in classical physics, you'd expect to see the atoms deflected randomly in all directions because their spins would be randomly oriented.
That makes sense. If the compass needles are pointing every which way, they'd get deflected all over the place.
But that's not what happens. Instead, the atoms split into distinct groups, each corresponding to a specific spin state up or down. It's as if each atom, before it was measured, was in a superposition of both spin states, both up and down, and the act of measuring forced it to choose one.
Wow. So it's like by observing these particles, we're actually forcing them to pick a lane. They're happy existing in this blurry state of possibilities until we come along and ruin the fun with our measurements. It makes you wonder, what else is possible in this quantum realm?
That's a question that has puzzled physicists for decades, and it leads us to perhaps the most mind-boggling concept of all quantum entanglement.
Okay, now you're just messing with me. Entanglement.
Yeah.
Is that anything like what it sounds like?
It's even stranger than it sounds. Imagine two particles linked in such a way that their fates are intertwined no matter how far apart they are. Measure one particle, and instantly you know the state of the other, even if they're light years away.
Wait, instantly? That seems like it would break the universe's speed limit. Doesn't Einstein have something to say about that?
You're right, it seems to violate everything we thought we knew about information traveling at the speed of light. Even Einstein called it spooky action at a distance because he struggled to explain it. But here's the thing, it's been experimentally verified time and time again. Entanglement is real.
Okay, I'm going to need a minute to process this. Entanglement. Particles linked across, like, the entire universe, knowing what the other's doing instantly. That's some next-level stuff.
It's definitely one of the most mind-boggling concepts in quantum physics, and it really challenges our everyday understanding of how things work. I mean, we're used to thinking about things being separate, independent, but entanglement suggests this deeper connection, this link that goes beyond what we can even really picture.
Yeah, it's almost like they're communicating faster than light or something, which doesn't even seem possible.
You're right, it seems to go against everything we thought we knew about the universe. Even Einstein called it spooky action at a distance, because he couldn't really wrap his head around it. But the thing is, it's been proven experimentally over and over again. Entanglement is real no matter how strange it seems.
So we've gone from light being both a wave and a particle to, like, the entire universe potentially being this giant web of interconnected particles, all because of entanglement.
Pretty much. Quantum physics has a way of turning everything we thought we knew on its head.
It definitely does. And it makes you wonder, what does all this even mean for us? Like, if the universe is this strange, this interconnected, Does that change how we see ourselves, our place in all of this?
That's the million-dollar question, isn't it? And it's something philosophers and physicists are still debating today. But one thing's for sure, quantum physics really throws a wrench into the idea of an objective reality.
So you're saying that we actually play a role in shaping reality just by observing it.
Yeah, it's not that we're just passive observers, separate from the world around us. Instead, the very act of observing, of measuring, seems to actually influence what we see.
Wow, that's a pretty wild thought. So it's not just that we can't know everything for sure because of things like the uncertainty principle, but our very presence, our choices to observe something, changes how it behaves.
Exactly. It's a concept that some philosophers call epistemological idealism. Basically, it's the idea that we can't separate what we know from how we know it, that our perception of reality is always influenced by our own minds and senses.
That is a mind-blowing concept. But it's also kind of empowering in a way, isn't it? Like if we're not just passive bystanders in the universe, if our observations can actually have an effect on reality, what does that mean for us? What are the possibilities?
It's a question without easy answers, but it definitely opens up some exciting possibilities. Maybe it means we have more agency than we realize, more potential to influence the world around us, even on a quantum level.
Wow, so if we take anything away from this deep dive into quantum physics, it's that reality is a lot stranger and more mysterious than we might think. We've got particles that can be in two places at once, spooky action at a distance, and the possibility that our very observations can shape the universe around us.
And the best part is, we're really just scratching the surface here. There's so much more to discover, so much we still don't know about the quantum world.
And on that note, it looks like we've reached the end of our deep dive. But this isn't really an ending, is it? It's more like a beginning to keep asking questions, to keep exploring, and to always be prepared for the unexpected when it comes to the quantum world.
Absolutely, because if there's one thing quantum physics teaches us, it's that the universe is full of surprises. And sometimes, the most mind-blowing discoveries are the ones we never saw coming.